says here, IR alone cannot determine a structure. Some signals may be ambiguous, but here's the big deal. The functional group is usually indicated, and 3 and 4 are probably the most important. The absence of a signal is definite proof that the functional group is absent. Correspondence with a known sample's IR spectra confirms the identity. So there is software and IR experiments where we just call it a computer algorithm. Nowadays they call it AI, but it looks at the unknown sample and looks at a database and looks at the two signals and figures out a probability that they're the same by analyzing the signal. So a machine sometimes analyzes things as being a fingerprint. It is a fingerprint. On to the next great thing, mass spectrometry. What do we do with mass spectrometry? We can determine molecular weight, and we'll find out we can also determine a molecular formula. Maybe in general chemistry you did a calculation where a sample underwent combustion analysis, and you had a mass of the sample, mass of CO2 that came off, mass of H2O, and you could figure out an empirical formula for any hydrocarbon, carbohydrate, those three elements, carbon, hydrogen, and oxygen. Nowadays nobody does that, but mass spectrometry can give you a very good empirical formula. The technique is destructive. The sample cannot be recovered. It's almost a non-destructive technique in that you only need a tiny, tiny bit of sample. Things working. So this is just one type, the most common type of mass spectrometry. Mass spectrometry can be, there's all different types. Can be classified on the ionization method and the mass analysis method. So the most common and the earliest is called electron ionization, where a beam of high energy electrons breaks the molecule apart. The masses of the fragments and their relative abundance reveal information about the structure of the molecule. So how does electron ionization work? You have some molecule and you fire electron at it. It has enough speed and kinetic energy that you get 2 electrons out. So you get this thing that has a positive charge, a radical cation. And this is done in a high vacuum environment. And then once you form this cation, you can do a bunch of neat physics things like accelerate it, make it bend. It has a charge. When a molecule loses 1 electron, it then has a positive charge and 1 unpaired electron. This ion is therefore called a radical cation. One thing I like about mass spectrometry, we get to use integers, numbers. For example, looks like I have ethane, C2H6. 2 times 12 is 24, plus 6. That's looking like 30. So slam an electron into that, 2 electrons come out. We don't worry about that anymore. So here's this thing called the molecular ion. And when you do this, it really imparts a bunch of energy. So after that, various things can occur. Here would be a radical proton leaving. And so this would be a fragment. So we might detect something that has a mass to charge ratio of 30 and something that has a mass to charge ratio of 29. Of course, something else can happen to this. If it cleaves right here, we could detect a methyl fragment at 15, and these radical things aren't detected. So other fragments can be formed when a carbon-carbon bond or a carbon-hydrogen bond are broken during ionization. Only the positive fragments are detected in mass spectrometry. Well, this particular form, there's probably a form of mass spectrometry that works on negatively charged. So you put some sample on this probe and you put it into this high vacuum situation. There's something that makes an electron beam. The electron beam hits the sample, you make those molecular ions. There might be some accelerating plates. Potential difference imparts kinetic energy to the molecular ion, and this thing flies down through this magnet. And then all those rules of physics take over, and some ions are kind of heavy and they just slam into the outside of the instrument. Some are too light and they bend too much and slam into the inside of the instrument. But the ones that are just right come through and they go through a detector, and you get a blip whenever that happens, a count. And so these are set up in such a way we can vary the magnetic field or maybe vary the acceleration. And so here is what a mass spectrum looks like. On this axis, you're going to have mass to charge. On this, you're going to have abundance. And you get these peaks corresponding to different amounts of mass to charge. So the most common mass spectrometer separates ions by magnetic deflection. The mixture of ions is accelerated and passes through a magnetic field where the paths of lighter ions are bent more than those of heavier ones. By varying the magnetic field, the spectrometer plots the abundance of ions of each mass. The exact radius curvature of an ion's path depends on its mass to charge ratio, which we symbolize m over z. In this expression, m is the mass of the ion in atomic mass units. Z is its charge. It says here the vast majority of the ions have a +1 charge, but many times there'll be a +2, +3. So we consider their path to be curved by an amount that is dependent only upon their mass. So let me have my fun here. 1, 2, 3, 4, 5, 6, 7. C7, 14, 16. 7 times 12 is what? How about? Should have just looked up here. All right, you can see a little blip there, and that's the molecular ion. This isn't nice. We don't have to go 12.011. And then this thing here might do something like this and say it has a plus charge, and there's the radical electron. It's got an unpaired electron somehow because we threw one at it, 1 electron and 2 electrons came out. So once this thing has a charge, it can be accelerated. We detect this. The highest thing detected is typically the molecular ion, or we call the parent peak. Corresponds to the molecular weight of the original molecule. And it's going to be the highest mass, because there's nothing else we're sending down the mass spectrum. And then we see some peaks. And the base peak is whatever's the most abundant, and the machine through software says we're going to call that 100%. Everything else is based on that. So here's a relative abundance. We might say there's some fragmentation pattern here with what we're seeing. So in the world of analytical chemistry, there's all these hyphenated things. GCMS. GC stands for gas chromatography. And now that you did the TLC lab, you've all been exposed to chromatography. What is that? It's a separation science. So you can take a sample, inject it into this small little tube, and there's a carrier gas. That's like your mobile phase. Here's this column. It has some type of packing, or it's coated with like something like wax. And so the sample partitions between being in the stationary phase and the mobile phase. And you can separate a sample out into all its components. And then it runs through this thing called a mass spectrometer. And every component, you get the molecular ion in a fragmentation pattern, and you can typically tell what it is. The gas chromatogram column separates the mixture into its components. The mass spectrometer scans the mass spectra of the components as they leave the column. I don't think I got the cool graphic I wanted, but anyway, one more. So there are places that do high resolution mass spectrometry. And I got too carried away talking about how mass spectrometry is nice. I just sum up energy weights. Here we have something, and we don't have energy weights. We're going to use all the weights off the periodic table. So here is propane. Don't know what that is. It looks like there's a degree of unsaturation there. Here's carbon dioxide. Here's something else. Now notice these all have a mass of about 44, right? Here's 44.06 something. Here's 44.026. Here's 43.98983. Here's 44.0. So in high resolution mass spectrometry, we can measure with an accuracy of 1 part per 20,000. That's pretty good. So a molecule with a mass of 44 could be propane, C2H4O, CO2, or CN2H4. And if we use high resolution mass spectrometry, the exact mass can be found. So when I was a graduate student, I worked in a mass spectrometry center the first year, and people from all around the country would send their samples there, and they would get this high resolution analysis. And there was an old timer there, and he wrote a program in Fortran, and it would go through the periodic table, and it had the exact masses of everything. It would come up with the most reasonable empirical formula, or we could even call it a molecular formula. If we have it would be the actual molecular formula. It would fit all the different possibilities. And that's how a lot of molecular formulas are determined today, using high resolution mass spectrometry. So you might have learned in general chemistry, where does the atomic mass unit come from? It comes from assigning an atom of carbon-12 an atomic mass unit of exactly 12. So this is by definition, and it's our standard. And then with a high-resolution mass spectrometer, if we call carbon-12 12, and then all these are based off everything else. So here is a certain isotope of oxygen, oxygen-16. Well, there's some other isotopes. So on the surface of the Earth, we say isotopes are present in their usual abundance. Carbon has a carbon-13 isotope present in about 1%. So that means when we do a spectrum, we see a little blip right above the molecular ion peak, and we call that the M+1 peak. And it'll be about 1% of the other height. In fact, maybe on Wednesday's lecture, we will see how that M+1 peak can be used to give us the number of carbon atoms in the compound. Bromine has 2 isotopes, bromine 79 and bromine 81. 79 and 81 average to about what? About 80. And if you look on the periodic table over there, you see 79.9. So that's the atomic weight is the weighted average of all the naturally occurring isotopes. So there is no bromine atom that weighs 80. Half of them weigh 79, the other half weigh 81, well, in whole numbers. So the abundances are almost equal. So you're going to see a molecular ion peak, and you're going to see an M+2 peak, and they're going to be about the same height. So looking at some other elements, well, there is deuterium out there. I don't know why. Well, in compounds, I guess we don't see much deuterium, but I'm told the ocean is full of deuterium. Don't know what to make of that slide. And of course, these sum up to 100, but there's got to be some carbon-14 out there. We won't worry about that. Nitrogen, mostly nitrogen-14. There is some nitrogen-15. Oh, here, oxygen. 99.8 of it is oxygen-16, oxygen-18, about 2% there. So sulfur, we have 3 isotopes. Sulfur-33, sulfur-32, sulfur-34. Here's the abundances. Here's the bromine. 50.5% 79. 49.5 is the 81. Chlorine's kind of interesting. 75% is chlorine 35. 24.5% is chlorine 37. So when you have a compound and you take the mass spectrum of it and you see 2 peaks, highest over here to the right, probably look at that and say this is M+1 and this is M+2. And so this is a bromopropane, and here's what the mass spectrum would look like. So I can probably sum up the whole integer values for all these carbons and hydrogens and add 81 to it and get this peak. Sum up all the carbons and hydrogen integer numbers and add 79 and get that peak. When you see these two peaks about the same height, you know you're dealing with a bromine. So here's chlorine, and so there's the molecular ion peak. That little blip is the M+1 peak. That little thing there is probably due to carbon-13. And then here's this thing, and we say that's due to the other isotope of chlorine. Chlorine is a mixture of chlorine-35, relative abundance about 75%, and chlorine-37, relative abundance about 24.5. So the molecular ion peak is 3 times larger than the M+2 peak. Here's sulfur. It had those 3 isotopes. We see an M+2 peak that is larger than what we'd normally see, and we attribute it to isotopes of sulfur. So let's look at some hydrocarbons. That's what we deal with a lot in organic chemistry. Here is hexane. So once again, if I go 12 times 6 plus what, 14? 6 twice is 12, 2 more, 86. There's my molecular ion peak. So it goes in the spectrometer, and it's just been shot with a beam of electrons, got an electron knocked out of it, it's got a lot of energy, it fragments. And so here's an M-15, here's an M-29, here's an M-43. So 86 minus 15 is 71. 86 minus 29 is 57. So these are losses of carbon fragmentations. If it fragments here, if it fragments there, or if it fragments right there. And maybe we could do some statistical analysis and say, why is the 57 the most abundant peak, which we call the base peak. So when I look at mass spectra, I notice for most hydrocarbons, the molecular ion is always even. And notice the fragments are odd. And you see that a lot. In fact, you want to be aware of that, because if you see an even and an even, it's going to tell you something. If you see an odd, that's going to tell you something. So here's kind of a breakdown. And so this is our molecular ion. It's in brackets. It's got a positive charge, and it can break apart. So it can lose an ethyl radical, isn't detected. This thing gets detected. It has a mass to charge ratio of 57. Or if we fragment in the same position, but we make this the radical, what's not detected, and we detect this, then we get the 29. So here's something interesting to look at. This is also C6H14, isn't it? And so we have this peak here. But our fragmentation pattern is a little different. And so here is an interesting peak. Our base peak is at 43. Let me just back up here. Here our base peak is at 57. And so when I think about it, and cleave here or cleave here, there's 2 positions there. That's pretty probable. Maybe that's how I'm going to rationalize that being the base peak. 43. And I might go pull out my calculator and go 86 minus 43. That's 43. I didn't need my calculator for that. Possibly you can say, well, Eric, if it fragments here, you can get a secondary carbocation. That's kind of nice. I go back and look at some of these. Primary carbocation, well, we don't know, but this branching probably makes a nice place for this thing to cleave right here. And I got excited. I knew this slide was coming up because I put them together the other. Same molecular weight, little different fragmentation pattern. And if we think about cleaving these for a second, we'd only have primary carbocations. Here we cleave right here. We're definitely going to have a secondary carbocation. That's why we have this different base peak. And here it is. We could lose a methyl. That explains the peak at 71. Or we could cleave here, and then this thing leaves as a radical, and that gives us our base peak. So aren't you glad you studied carbocation stability first semester? Probably resonance structures. When I got to graduate school, I thought mass spectrometry was the coolest thing. It's like, Organic chemistry in the gas phase. Woo! Now let's go back and notice my 71 peak. That's loss of a methyl here. Gives me a secondary carbocation. Methyl here or here, I'm going to have a primary carbocation. So, you know, nature doesn't like primary carbocations. So I think this fragmentation pattern has more to do with statistics. You know, it can break here quite often. These are equivalent either end. And I got 2 positions here and just 1 here. Suppose I got 2 positions here. But anyway, this peak and this peak, we can definitely rationalize those being higher based on carbocation stability. Resonance stabilized cations. So we have an alkene group here, and I believe at some point last semester we talked about the allylic group. It's a real stable carbocation due to resonance. That double bond can move over there, so it can delocalize that positive charge. Fragmentation in the mass spectrometer gives resonance stabilized cations. Whenever nature can do it, it's going to do it. The most common fragment of an alkene is cleavage of an allylic bond to give a resonance stabilized allylic carbocation. You know, this chain could be going on out further. We'll make this a methyl group, make this go out on further. Nature's going to want to cleave this right there to form this resonance stabilized allylic cation. So here's hexene. Once again, an even molecular ion. All the fragmentations are probably going to be odd. And there's no allylic group. Right here's the allylic position. So if we cleave that, we're going to lose 29. And I feel half brain dead. 84 minus 29. What do I get? I get 55. That's due to this cleavage going on there. Here's a benzene ring. If I have this as an alky group, we call it the benzyl group. And the benzylic carbocation is one of the most stables. You know, here it looks like a primary, but it's way more it's way more stable than any primary carbocation because, well, now that's in a secondary position, but it gets charged, localized, delocalized over that whole ring complex. Compounds containing aromatic rings tend to fragment at the carbon next to the aromatic ring. There's the carbon next to it, likes to fragment right there. Such cleavage forms a resonance stabilized benzylic carbocation. So alcohols often lose water. So the molecular ion is going to have an even mass to charge peak, and notice this is even. So I said earlier, notice that the molecular ion is normally even and then all the fragments are odd. Here you see something like this, it's kind of going to scream alcohol at you. And the isotopic abundance of oxygen, depending on your machine, you may not notice that. But if you notice another even peak, 18 mass units below your molecular ion peak, that probably means alcohol. And then notice this is like elimination, how we do hydration of an alkene to an alcohol, dehydration of an alcohol to an alkene. So remember my excitement, organic chemistry in the gas phase. So here's 3-methylbutanol. And one thing to note about a mass spectra, sometimes nature won't necessarily give you a molecular ion peak. The arrow is almost obscuring, eclipsing the little tick mark, the little blip. So here's our little blip at 88, and then we see this other peak at 70. We want to go 70 and 88. What's the deal with those two peaks? Well, they're both even, and the difference is 18. And man, well, sorry about this graph. Here's our base peak. So where'd this peak of 70 come? Here's our molecular ion. We can lose water and form this thing. There's our peak at 70. Notice once we form this, we have these 2 allylic bonds. Chop one of these off, and you get this thing. And this thing is relatively long lasting compared to the others, so it becomes our base peak. Something we see there.